Okay, so here's where we're at. So you got four fundamental forces. You got
Gravity.
gravity, which is going to be part of the lab today.
Black.
Magnet. Pretty sure you
Hold
said
on.
magnet.
So there's two ways you can calculate the gravitational attraction between two objects. This is the big one, okay? F equals big G M1 M2 squared. So if we wanted to calculate the gravitational attraction between
Me and the chair.
Louise and the Earth, okay? Here's one thing we could do. This is just a number, don't worry about it for now, it's 6.67 times 10 to the negative 11. It has units of newtons, meters squared, or kilograms squared. Okay, it's called the universal gravitational constant. It's universal, no matter where you are in the universe, hence the term universal, okay? And then we could plug in the mass of Louise, we could plug in the mass of the Earth, and then what we do is that we treat the Earth as what we call a point mass. Like all of the Earth is concentrated into one point right at its center. So if we knew these two numbers, okay, mass of Louise, mass of the Earth, how far apart Louise is from the center of the Earth, we could calculate the value of that force. If we were to calculate the attraction between Louise and the moon, all we'd have to know is Louise's mass, the mass of the moon, distance, okay? You can do that. Typically on Earth, we can do this, but it's a very, very complicated calculation. Because you've got to have the mass of the Earth, the distance from the Earth, and it's complicated. You can do it that way, but it's complicated. The simpler way to calculate, say for example, here is a 200-gram mass. So one option to calculate the gravitational attraction between this 200-gram mass of the Earth is to go to this equation and plug in 0.2 kilograms, mass of the Earth, distance from the center of the Earth, big G. It's a complicated thing. You can do it, but it's complicated. Now, there's a simpler way. Because at the end of the day, and later on you see there's a hidden truth to this equation. What we're going to do is we're just going to take this mass, whether it's Louise, whether it's 2.2 kilograms, whatever it is, and we're going to multiply that by the gravitational acceleration. So this is one of the skills that you've got to be able to do without fail. It's not a big deal. You're just going to take 0.2 kilograms times 9.8 meters per second squared, and you're going to get 1.96 newtons, okay? So one way to determine the weight of an object is to take its mass times the gravitational acceleration, okay? That's option number one. Now, the other thing that you can do to find the weight, notice I did not say mass, I said weight. Weight in a physics class is just going to be measured in newtons. Weight is not pounds, weight is not kilograms, mass is kilograms, okay? And we will never do anything in pounds, okay? Ever, ever, ever. If you find yourself trying to answer in pounds, stop, get help. You've missed the entire point of the lecture. Now, the other thing that you can do, is this is what we're going to use in the lab today, is this handy dandy meter, okay? So it's simple, it measures in newtons directly. You don't have to multiply anything by 9.8 meters per second squared. It's already calibrated to be on Earth. Obviously, if you take this to the moon, it won't work because it would be off because G on the moon is like 1.7. So here's how you use this. So what you want to do is hold this in the direction that you're going to use it. So sometimes in this lab today, you're going to be lifting things up. Hold it like this, it should be reading 0. Other times in the lab today, you're going to be like pulling a block. So if I'm pulling a block, I'm going to use this thing horizontally. But if you notice, when I lay this thing horizontally, the scale reads negative 0.08 newtons, which isn't 0. So what you want to do is take the scale, put it in whatever angle you're going to use it, and then there's a 0 button over here, okay, it just says 0. Just press that button one time, and now the scale is going to go back to reading 0. So it's kind of like a scale that you use in chemistry where you press like the tare button to re-zero it. That's what that zero button does. So put it in whichever angle you're gonna use this thing. If it isn't reading zero, press the zero button, it'll go back to that. So, now I'm gonna lift this thing up, so now I changed that, so now I need to hit that zero button again. So the other option is that I just lift this up. So I lift this up, and it reads, oddly enough, well, 1.95 newtons. Should read 1.96, hey, we're off by 100th of a newton. So there's two ways you can find the weight of anything. If you know its mass in kilograms, multiply that by 9.8 meters per second squared. Or you just take a Newton scale and you lift it up. Is somebody out there?
We don't do chemistry this semester.
Oh, God.
He's on here.
No, it's not. Thanks for asking, though. So, those are the two ways. There's actually three ways. The third thing you can do is this big monstrosity of an equation, but we won't do that, okay? So we're either gonna take the mass times 9.8 meters per second squared, or we're just gonna use the Newton scale. Those are the two ways. Now, the next one that we'll talk about is the electromagnetic force. In AP Chemistry 2, we'll spend a lot of time talking about this one. Do not worry about this equation. All I'm doing is pointing it out. All this is saying, hey, here's the force of either attraction or repulsion between two charged objects. If they're positively charged, they repel each other. If they're negatively charged, they're going to attract each other. But here's the thing. Whether you're talking about gravity, you're talking about the attractive, technically this is called Coulombic force of attraction or repulsion, if you don't want to get technical. But here's what's important. As the charge gets bigger, the force gets bigger. As the distance gets bigger, the force gets smaller, okay? So in that regard, it's like gravity. Oh, the bigger the mass is, the stronger the gravitational force is. The bigger the distance is, the smaller the gravitational force, okay? But this only works with charged particles. Like if you have neutrons, this equation won't work because the neutron doesn't have a charge. So the electromagnetic force of all the forces is the most diverse, okay? And without the electromagnetic force, we would not be here having this discussion. Because without the electromagnetic force, atoms don't bond together. You don't have DNA, you don't have protein, you don't have amino acids. Oxygen doesn't bond to the hemoglobin in your blood, and that oxygen gets carried to your cells, okay? We don't have a universe without the electromagnetic force. So if you look at chemistry, oddly enough, if you remember like the diatomic molecules, like for example, hydrogen, nitrogen, remember those from Chem 1, hydrogen, oxygen, fluorine, okay? So even if you look at something as simple as hydrogen, which is the most abundant element in the universe, oh, hydrogen gas. If you think about it, there's two opposing ideas. So hydrogen, most of the time, is just a single proton with a single electron. So there's St. Bernard and Chihuahua. Okay, that's it. So there's the St. Bernard, there's the Chihuahuas. So here's the odd thing about hydrogen being diatomic, if you think about it. You have two protons. They don't want to be near each other. They want to go flying away. Cool. They don't want to be near each other. You have two Chihuahuas running around. They don't want to be near each other. Okay, they don't. Now, is this Chihuahua attracted to that proton? Yeah. So the Chihuahuas are attracted to the St. Bernards. But you have a whole bunch of things that don't like each other. Two protons that don't want to be near each other, and two Chihuahuas that don't want to be near each other. But yet, they form a very stable bond. They're actually more stable together than they are separate. And that's what science tries to answer, is like, whoa, what happens? Well, clearly, since Mother Nature is the lazy prima donna, this has to become more stable. So without going through a whole discussion on wave functions, basically what happens is that those waves, the electron paths overlap. And by overlapping, that creates a more stable molecule than the two hydrogens separately. So even though they don't like each other, it becomes more stable, and that's why it's diatomic. It's not triatomic. There isn't like three hydrogens. Notice we never have triatomic molecules. At both we have diatomic, nitrogen, oxygen, fluorine, bromine. So that's what chemistry basically tries to answer. So chemistry deals with the rearrangement of chihuahuas. Okay, that's it. Your body produces energy by rearranging chihuahuas. Okay, and out of that byproduct of on the cellular level, you get two byproducts. You get carbon dioxide, water. Okay, that's when you breathe out two things. You breathe out carbon dioxide and you breathe out water vapor. Okay, you don't believe me when it gets cold and you're outside and you do this and it condenses. That's the water that's coming out of you as a byproduct on the cellular level. So every cell in your body functions by rearranging chihuahuas. That's it. If your body can't rearrange chihuahuas and produce energy, bad things are going to happen. Okay? All right. Now, if you look at what we've done as a species, one of the coolest things we've done is figure out how to manipulate the electromagnetic force. Let's say, for example, you're outside, and this is when you actually participated in life, and you were playing football or tag or something like that, and you ran on the grass, and you got like a grass stain on your knee, okay? Right? This is back when you all had fun, right? Now you're like, okay, I'm still having fun. And you would go out and you would have fun, and you would ride your bike and enjoy life. Back before TikTok and cell phones. So you put it in the laundry, right? And you add soap. What's the function of soap?
Clean.
By doing what?
Get rid of the
Breaking
dirt.
down
How? What do you have to do? Elliot, you said it.
breaking down the things on the things so that it,
You go, okay, let's get a little bit more specific than breaking down the things on the things.
like the mud and things on the towel,
Okay?
so that it can be removed more easily by water.
So here's exactly. So what the soap does is that the soap breaks the bonds that holds the stain to the cloth. Okay? But it doesn't break the bonds that hold the cloth together. It isn't like, hey, I throw my jeans in the machine and I wash them, and you open it up, it's like, where'd my jeans go? Oh, well, they're clean, but they're gone because they dissolved. So the function of soap is to break the bonds that hold the stain to the clothes, but not break the bonds that hold the clothes together. Think about the act of writing. Okay? Here's your pencil. There's your paper. How does that work on an atomic level? What happens?
The graphite starts breaking off onto the paper.
Okay, so you have to break the bonds that hold the graphite together. Okay, so we have to have enough of a bond to hold the graphite together and make it a solid. Okay, which is basically just carbon. Graphite is carbon. So you have enough bond to hold it together. But then you write on the paper. Then what does it do?
Breaks.
It breaks the bonds that hold the graphite together, but then it bonds with the paper. Okay? Now, it isn't like, and then it sticks to the paper. It isn't like you lift up your paper and all the graphite falls off. It's like, Mr. Burkamp, I swear I had my assignment done. I lifted it up and all the graphite fell off. Okay? My bad. Okay? No, it sticks to the paper. Now, God forbid, hypothetically, you write the answer 4 and you realize, oh man, it should have been 6. What do?
Erase it.
Erase it. So how does the eraser work?
Break the bonds between
The eraser breaks the bonds that hold the graphite to the paper. So the act of writing with graphite seems elementary, but on an atomic level it's complex. Now, you take those same graphite and those carbon atoms, you rearrange them differently, you get diamond. Okay? Same carbon atom, you rearrange them differently.
Don't you have to compress it?
Oh, immensely, and under extremely high pressure. It isn't like, oh, I'll take some graphite, put it in my hands and smash it. It's like, oh, look, diamond, here, okay? But then what do you know about diamond in terms of the hardness of diamond?
Pretty hard.
Yeah, it's one of the hardest substances on Earth. So you take carbon atoms in one arrangement, you can write with them. You take carbon atoms, you arrange them a different way, you have one of the hardest substances on Earth. Still carbon atoms. Can you see through graphite?
No.
No. Can you see through diamond? That's the whole point of it, right? So in one structure, it's soft and you can't see through it. Another arrangement of carbon atoms, you can see through it and it's a little hard. Kind of cool if you think about it. So how this is going to impact us. The electromagnetic force is what allows us to exist. So when you wash your hands, do you worry about your hands becoming soluble and dissolving in the water?
Yes.
Sometimes, okay? Ever happen? No, thank God. It's like, what happened? I washed my hands and my fingers fell off. Okay? You don't have to worry about that. So, but here's the cool thing. So you have these atoms that hold your skin together. They don't like each other, even like when you clap my hands. I don't have to worry about the atoms in this hand sticking to the atoms on that hand, which would be really weird. It's like you pull your hand apart, it's like, oh man, now I have 6 fingers on this side and 4 over here, okay? You don't have to worry about that. Even within the same hand, you can do this, one hand clapping, right? The atoms that make up my fingers don't like the atoms that make up my palm, okay? You don't have to worry about that. So they stick together, which is cool, because if they didn't stick together, we wouldn't be here having this discussion. But yet, they don't like each other. So here's the weird thing. On an atomic level, nothing ever actually touches, depending on how you define touch. Because if you look at a carbon atom on scale, here's that nucleus, here's this huge electron cloud. So when you take that carbon atom and you touch it on paper, all that's happening, anytime you touch anything, all that's happening is an interaction of electron fields, okay? The electrons themselves don't touch. Because remember yesterday, and I had the 2 charged balloons, and I tried to put the 2 balloons together? They were having no part of it. Same thing happens with electrons. Electrons don't like each other. But yet they bond together, and they form DNA, and they form Oreos, and they form squirrels, okay? So if atoms didn't link together, we would never be here having this discussion, because you cannot have a universe that atoms that don't link together. Okay, so what's going to impact us is going to be friction, okay? So friction, and this is going to be the focus of the lab today, friction is created by interactions of basically electron clouds. So when you move your hand past each other, that generates some heat, okay? You've all been outside, you've lost your mittens, and it's cold. What do? Put your hands together, right? You generate heat. So the interactions on the electromagnetic force that's holding your hands together can also generate heat. Now that heat is photons. So what you feel, oddly enough, is a photon. Like, oh, right, heat to photons. Remember the very first day we took the barometer, and we wrapped my hand around it, boom, that water went right up. Because the photons from my hand were interacting with the gas particles. That was the electromagnetic force. That was all, excuse me, that was all about the electromagnetic force. My hand was emitting photons. The photons were interacting with the nitrogen and oxygen inside the glass. That gained in energy. That interacted with the water, and it pushed the water level up. Everything that happened in that example was the electromagnetic force. You want to make toast, electromagnetic force, okay? You see things, electromagnetic force. So electromagnetic force in general is the broadest of all of the 4 fundamental forces. Third one, strong nuclear force. The only thing you have to worry about the strong nuclear force is that it holds the nucleus together, and it's the strongest force. If I ask you, what is the strongest force? Do not miss this question. It's the strong nuclear force. Now, the weak nuclear force is important. We'll touch on it in AP Physics 2 when we do nuclear physics. Don't worry about it for now. It's important. I'm not trying to discount that. Without the weak nuclear force, we would not be here having this discussion, because without the weak nuclear force, hydrogen doesn't fuse into helium, and our sun doesn't produce energy. So the weak nuclear force is vitally important. It's just not something we're going to study. Okay? So you got to worry about gravity, electromagnetic. Those are the 2 that manifest your life. You drop something, oh, that's gravity. What keeps it from falling through the floor? Oh, that's the electromagnetic force. Okay? Strong nuclear force is important. If you lose it, all of the atoms in your body, all the nuclei, are going to go flying apart. Okay? Which would be really, really weird. It's like, what happened? I don't know. Strong nuclear force stopped working. Really? That's bad. Okay? Weak nuclear force, don't worry about it. Okay. So, let's talk about a couple of different situations. So here I have this block of wood. How can I find the weight of this block of wood? What are the two things I can do?
Measure it with the,
Measure how much we have.
Take the Newton scale, okay? Now, I'm gonna be lifting that up, re-zero it. Lift this up, I get 3.90 newtons. So when this block sits here, gravitational force is 3.90 newtons. Now, I'm gonna make that negative, okay? So if I just lift this up and I drop it, what's the only force acting on it?
Gravity.
Gravity. And that gravitational force is gonna be negative 3.90 newtons, okay? Boom. But it's sitting on the table. It's not accelerating. So what does that mean?
Force is equal to.
Forces add up to equal to zero. So what's balancing out that negative 3.90 newtons?
The normal.
Tables, okay? What we're gonna call, what Elliot said, we're gonna call that force normal, which in this case is gonna be positive 3.90 newtons. Now, this will play out large later on when we get into inclined planes. We're not on inclined planes right now. But technically, force normal equals Fg cosine theta. But we're gonna be on flat surfaces for now. The cosine of 0 is 1. Don't worry about it, okay? We will later. We're just not gonna worry about it now. So if that's negative 3.9, the normal force is gonna be 3.9. All the forces right now add up to
Zero.
0. Is it accelerating? No, because all the forces add up to equal to 0. Remember, every force problem you're gonna have can only do one of two things. It's either constant velocity or you have accelerated motion. That's it. That's it. And if it's accelerated motion, what are your two options?
Speeding up. or
Speed up,
slowing
slow down. That's all I can do with any force problem. Any force problem, I only have three options. Speed up, slow down, constant velocity. That's it. Make the forces add up equal to 0 or they don't. Now, drawn like this, and you got to get used to the vocabulary. Drawn like this is what we call a free body diagram. You treat the block as a point, and you draw all the forces acting from them. This is not tip to tail. This is a free body diagram. Now, if you were to draw it tip to tail, you'd have your force normal going, that's actually the gravitational force pointing down, and then you'd have your force normal. Where do you end up? Back to the origin. Is there a resultant?
No.
No. Therefore, you are at
0.
0 what?
Zero. Force. Zero.
0 net force. There's forces,
Yeah.
but there's just no net, what we call a net force. Net force is what creates an acceleration. There's no resultant. Now, if all the forces add up to equal to 0, does that mean the object is at rest?
No.
No, all it means is that you have a horizontal line in your velocity time graph, okay? You're just not accelerating. So, let's talk about Newton's laws of motion. So this is sitting here. Cool. I want to make it move. What am I going to have to do?
Push it.
Push it. I got to apply a force to it, okay? Because if I don't apply a force to it, Mother Nature goes, hey, I'm chilled out, wearing my tie-dye, my Birkenstocks, hitting the hookah pipe. I'm not doing anything. It's a Friday morning. If you think I'm going to make that block move, you're nuts. You want to make it move? Hey, you do it. So, I pull it along, right? Now, here's what's going to be important in 2 words. I'm going to pull this thing at a constant velocity. So as this thing is getting pulled, I'm going to pull it at a constant velocity. If you're at a constant velocity, the sum of the forces adds up to 0. So now, when I pull this thing in again, I'm going to use the scale, but now I'm going to use it horizontally. So I'm going to re-zero the scale, so it's reading 0. So I'm going to pull this thing along at a constant velocity. That takes about 1.20 newtons, okay? So we got it. So now we're going to change the dynamic. So now I'm going to have some force applied. which in this case is 1.20 newtons. Okay? Force supply can come from a squirrel, a rocket engine, a sail, a fan, something external that's making the cart move. Right now, if I added up all of the forces, what would it add up to?
Not 0.
Not zero.
0.2 and
It add up to 1.2 because I've got a negative 3.9, a positive 3.9, and 1.2. Right now, the forces do not add up to,
Zero.
which means it would
accelerate.
accelerate. But it's not accelerating. So what does that mean?
Friction.
What that means is that we have to pay off the frictional mafia. So the frictional mafia, Big Tony, basically says, you gotta pay us a little bit of tribute. So the frictional mafia says, you wanna move the block, that's cool. You've gotta pay us $1.20 newtons. Now does everything add up to equal to zero? Cool, it does. Now everything adds up to equal to zero. And now you're at a constant velocity. So, drawn like this, and this is one of the diagrams you're going to draw on your lab. These are drawn to scale. When I tell you to draw a free body diagram, unless I explicitly tell you to sketch it, that means you draw it with a ruler. So these are fairly big, so you could let like 1 Newton equal a centimeter. If they were smaller values, you could like let 2 centimeters equal a Newton, so that you're not trying to draw tiny, tiny little vectors, okay? Even with this, you might even consider letting like 2 centimeters equal a Newton, because otherwise, like trying to draw that 1.2 is gonna be really, really small. So, when I tell you to draw free body diagrams, and I'm gonna tell you to draw a lot of free body diagrams, unless I explicitly tell you to sketch it, you get out a ruler and you draw it to scale. You treat it as a point mass, all the forces acting from the center of that mass. Second diagram you're going to draw is the tip to tail. Okay? Now, personally, what I always do, I always draw my gravitational force first, and then I've got my force applied, and then I've got my force normal, and then I've got my force friction. Where do I end up?
Same place.
Back at the,
Start.
therefore I do not,
No,
A result.
no.
I don't have a net force, I don't accelerate, right? So when you draw forces tip to tail, you only have 2 options. You either end up back at the origin and you're at a constant velocity, or you don't end up back at the origin and you accelerate. Okay? Now, so I pull this thing along and then I stop pulling it. What happens? What do I lose?
Force applied.
I lose my force applied. What's still there?
Friction mafia.
Guess what? Then you accelerate, because then you don't end up back at the origin, because all the forces don't add up to equal to 0. So, on the lab, you're going to draw a diagram like this, tip to tail. You're going to draw a diagram like this, free body diagram, with a ruler to scale. Okay? Now, the next thing that you want to be able to calculate is what we call the coefficient of friction. So if you look on your equation sheet, and here's the dichotomy of the forces test. It's the longest unit that we're going to go through, but it's actually the smallest number of equations that are on this sheet. Okay, it really is. So one of the equations that you're going to need is down here underneath that big gravitational force equation where it says m1, m2 over r squared. So what you have on your equation sheet is this. The absolute value of force friction is less than or equal to mu times force normal. Okay? So, let me explain what all this stands for, because it looks like, wow, what is this? This doesn't make any sense. So, let's start with this. So this is your force friction, okay? So the dichotomy of the force friction is that we never measure force friction directly. We can measure how much force it takes to keep something moving, but don't come to me and say, hey, Mr. Burkamp, where are the force friction sensors? They don't exist. They do not exist. What does exist is I measure how much force it takes to pull it, and by measuring how much force it takes to pull it, then I know what the force friction is in the opposite direction. Okay, so don't come to me and say, hey, I can't do the lab. I don't have the force friction sensors. I can't measure it. Measure the force applied. By measuring the force applied, you know what your force friction is. It's like the mafia isn't going to come out and say, hey, you got to pay us $200 in protection money. What's going to happen is that you're going to talk to the store owner and go, hey, what's happening? I got to slip Tony $200. Okay? He's not going to explicitly say, this is the protection money I have to give to the mob. He's going to say, hey, Tony, here's $200 for the week. Okay? So by knowing that he's giving Big Tony $200, you know what the protection money is. Same thing happens with the force friction. You're saying, hey, I got to pay $1.20 to keep the block moving. Now you know what the frictional mafia is charging you to make it move. So this value here, it's a Greek letter. It's the Greek letter mu, so it's like the letter U, but it has like a curly French side off to one side. So this is the Greek letter mu. And this stands for the coefficient of friction, okay? And this F normal is just your normal force. And again, technically, your normal force is Fg cosine theta. For now, don't worry about the cosine theta part of this. So this is like the theoretical, big, long, drawn out version of this. Notice that these are absolute values. The reason that they're absolute values is because of the fact that typically what you're solving for, and this is what you're going to do in the lab, typically you're trying to solve for mu. Now, this is technically less than or equal to. We never worry about the less than part of it. You just always assume that these are just equal to each other. The less than is kind of the theoretical part of this. Don't even worry about it, okay? Just always deal with the equal sign. So typically what you're going to do in the lab is that you're going to take force friction and you're going to divide that by force normal. That's where it's applicable to put the absolute value signs. And here's the reason why. So if you go back up to the example that we just did, and we wanted to calculate the coefficient, this is what we call kinetic friction, because it was in motion. You have kinetic friction, which comes from the Greek word kinesis, which means in motion. So you have kinetic friction, which is in motion. You can also have static friction, which is from rest, which we'll talk about in just a second. So what I wanted to figure out is what's the coefficient of kinetic friction? What's this value? So if you look at this mathematically, and this is why there's an absolute value. Technically, the force friction on how we define the system is a negative 1.20, okay? Don't worry about it, it's just a number. So we're just gonna make that 1.20 newtons. Then my normal force was 3.90. So somebody get a calculator and take 1.2 and divide it by 3.9.
0.31.
0.3 exactly?
Yeah, 0.307.
0.307. Because everything here has three digits, that means this should have 3 digits. Quit rounding. Okay? Now, that doesn't mean you need to write that as 0.0375132. You know, you don't have to write out 10 digits because the oracle spoke to you and said there's 10 digits. Okay? Generally, you cannot go wrong with just 3 digits. What units does this have?
Point nothing.
Good.
It has no units. Why?
Newton divided by Newton.
Yeah, it's just newtons divided by newtons. Now, since you don't have any units, do you think this is a vector quantity or a scalar quantity?
Scalar.
Absolutely scalar, okay? This is why it doesn't make any sense to make it negative. Because it's a scalar quantity. It's just a ratio of forces. So there's a couple of things about mu, okay? So first off, it's one of the very few instances that mu has no units, okay? Because it's just a ratio of newtons, okay? So it has no units. Because it's an absolute value, mu is always greater than 0. Okay? Do not ever have a negative mu. It doesn't make any sense. Now, you'll also see that mu, it is exceptionally rare that mu is greater than 1. If you ever calculate mu and you get like 3.5, something has gone horribly wrong. Top end might be little over 1, okay? What we're always going to do is certainly going to be less than 1. So if you ever calculate mu and you get a big number, something has gone horribly wrong, okay? So, no units, it's never negative, rarely, exceptionally rarely, is it bigger than 1, okay? Got the idea. Now, what we just did is what we call kinetic friction, which is energy, which is in motion at a constant velocity. To get static friction, it's the same idea, but it's a little bit more of a technique. So static friction means from rest, okay? So what you're going to do is the same idea. You're going to take your block. Oddly enough, it's going to be at rest. Then you'll take your scale, and what you're going to begin to do, and I'm just doing this so that it's easier to see the camera. And what you're going to begin to do is you're going to increase that force. You're going to pull it harder and harder and harder, but you want to slowly increase the amount of force until it just begins to move like that, okay? So you're at rest. You're slowly increasing the amount of force until, bam, it just begins to move. So I'm going to go back to this surface. So that way I'm comparing that same thing. I'm going to pull this until it just begins to move, which was 1.30 newtons, okay? So, to calculate the coefficient of static friction, it's the exact same idea. It's still mu equaling the absolute value of force friction over force normal. Same idea, okay? So the only difference here is that now I'm going to take 1.30 newtons and still divide it by 3.90 newtons. So you do that, divide it out, what do you get?
3, repeating.
So 0.333. So theoretically, listen to me very carefully for that word theoretically. Theoretically, if all things are equal, your static friction is greater than your kinetic friction. Mainly because the block is at rest, you have bonding taking place at an atomic level, it wants to remain at rest. So theoretically, your static friction is bigger than your kinetic friction. In the lab, if you don't get that and you get your kinetic friction to be a little bit smaller, don't flip out and go, oh my God, I broke the universe. No, okay? You're going to be working on those tables in the back, and those tables do not have a completely uniform surface. So the variation could just be you're pulling it at a different spot on the surface, okay? So don't flip out and go, oh my God, we broke physics. You didn't break physics. It was just a different part of the table. Cool with that? Okay, so stop that camera. Let's go to the back. I'll show you what we need to do. Nick, so bring you on. Go.